Hello, welcome to this SimScale demo on FEA for early stage design. First of all, let me introduce myself. Hi, I'm Steve Lenne. I'm one of the application engineering managers here at SimScale. So the case that we're going to look at today is a robotic gripper, and we're going to look at a FEA analysis of this focused on an early stage type analysis that perhaps a design engineer would conduct. The objective is that before starting an official approval process, the designer wants to assess the uniformity of the deflection during grappling of the load. This is a new design for a gripper assembly, and it's a relatively complex assembly. We've got over 50 parts, and if the designer was to use ROARC hand calcs for this, it would oversimplify the situation. Because it's lifting equipment, we're going to be working to a 6 times safe working load for the lifting equipment. And essentially, we want to avoid having an expensive repeat of a proof load test at the end of the design cycle. So there's a designer in your organization saying, how can I assess the assembly? How can I assess these stresses quickly and accurately? And are my hand calculations that I've done correct? So to simulate this assembly, we're going to have a fixed constraint to the block or the boom of the crane, and we're going to apply a 200 Newton gripping force along each of the gripper bars. So let's have a look how we can do this in the platform. Okay, so here we are in the SimScale workbench. Something to note is I'm using a Google Chrome browser. All you need to access SimScale is a web browser. It's fully cloud hosted. So we're looking at the result here of a FEA simulation of this gripper, and we can have a look at the stresses that we've got. We're viewing the von Mises stress here in megapascals, and we can see that this component of the gripper has a stress concentration. So we can easily investigate what the stresses are in this component, and we can see that we've got a peak stress of about 9 megapascals here. We can easily investigate how the stresses are distributed within the part by adding cutting planes and having a look how deep the stresses actually go. So we can see that the stresses don't penetrate too deep. We can see that we've got a slightly higher peak stress here that we couldn't see without the cutting plane of 12 megapascals, but it's still well below the yield stress of 430 megapascals for this aluminium 7075 alloy. So the actual stresses that are present wouldn't be a concern to us here. But something interesting that's happening with this component is that this part is more highly stressed than the other. So we can see that there's not a uniform load distribution. So we could investigate this load distribution by actually looking at the displacement that we've got here. And we can scale the displacement by a scaling factor to make it more apparent and add an animation so that we can see how the part deforms. Okay, so we can now see the part deforming, and maybe we would want to orient our view so it's in line with these gripper bars. And we can see that the part is not deforming uniformly, and we're actually getting some torsion in the whole assembly. So this may have an impact on the actual gripper force and how uniformly it's grappling the load. We could also look at the part color here and change this to displacement to see what the total displacement is. So we can see the peak displacement that we've got in the component, and we could easily investigate this to see what that peak displacement actually is. So it's not huge. We've got 0.3 millimeters of displacement, but that could be sufficient to reduce the effectiveness of the gripper. Okay, so we've looked at some results here for this actual gripper assembly. Something to note is we've got in-product chat available. If you've got any questions about your analysis or your setup, you can always ask our support team. And all of your projects are your own proprietary information, but you can share your projects with our support team if you would like them to be able to see what you're working on by clicking this tick box. Also, you can share your projects internally. So in this example, we're considering that you may have design engineers creating simulations at an early stage in the process. Perhaps they would want to be able to share these simulations with the simulation team so that they can have a look at what the design engineers are doing and check the setup. So to do that, you can simply enter an email address in here and specify whether you want the user to be able to view, copy, or edit the project. Okay, so now I've shown you a bit of the analysis here. I want to show you how we can actually do a design iteration and set up a new simulation for this gripper. So the first thing we're going to do here is import a new geometry into the workbench. And to do that, we can drag and drop our geometry in. In this instance, we're using a step file, but we support most CAD formats. And this imports the step file geometry into the platform. So we can see the gripper assembly here. But before we create a simulation, I'm going to actually edit this geometry to create a design iteration. This is the component that was flexing and more highly stressed than the other. We can see it's already got a higher thickness, and I'm going to edit this further using CAD mode. Okay, so here in CAD mode, I'm going to edit the component by extruding this face by 0.005 meters. So we've actually thickened up that component. So we have a new geometry now with a design iteration that I'm going to create a simulation from. And we're doing a static structural simulation in this circumstance. This gives us a new tree in the workbench, and we can see that it's detected 79 contacts in the assembly. All of these are set as bonded contacts by default, but we can change those to sliding or another contact form. In this circumstance, that's fine to have standard bonded contacts. And just like in other simulation platforms, we're going to work down through this tree to get a green tick on all of the items. So the first thing we need to do here is assign materials. I'm going to assign aluminium in this case to all of the materials that we have in this assembly. And then the second step we need to do is go through setting the boundary constraints. So we have a fixed support at the top where it connects to the crane. And then the other boundary conditions, which are the constraints and loads on the part, are the forces that are going to be applied to the gripper bars. And we're going to apply the force to the bars that have the greatest bending moment from the fixed support. So that will be the bottom bars. So I'm going to assign it to this face, and we can see that this is in the positive Z direction. So we're going to apply 200 newtons on this face. And then we're going to apply another force on the bar on the other side. And this time it's going to be in the negative Z direction. So we're going to apply negative 200 newtons. So now we've actually set up all of the conditions. We've got our fixed top and the loads. And then we're going to actually just have a look at the mesh that we've got here. We're going to leave everything as default. So we're going to have the default fineness. The only change we're going to make here is we're going to apply second order elements. And we can see that this will take 6 to 12 minutes to mesh. So now we can set off a simulation run to actually analyze this assembly. And we can see that that's going to take about half an hour to complete. Now that's starting the mesh and it will run the simulation. The great thing about having this cloud-hosted solution is we can also run parallel simulations. So If we wanted to also look at how it would perform under a different load criteria, for example, we can immediately change our loads in here to 400 newtons and then set off another simulation run in parallel. So we could give that a separate name so that we know that it's the 400 Newton case, and it will run that simulation in parallel with the first one once the mesh is complete. So just going back to the original simulation for a moment now, let's have a look at the runs that we ran previously. The one that I looked at with you was the standard mesh settings with a fineness of 5, and that took 16 minutes to run. Even with the coarsest mesh settings, we would still get meaningful results. It would have taken 3 minutes to run. We would have got meaningful results, and we would have still understood that that was the highest stress region of the component. We just wouldn't have had the same level of detail. And this result would have been obtained within 3 minutes. 20 minutes later, after setting off those simulations, I've received an email to say that my simulations are complete. So we can see here that both of the runs that we set off have successfully completed. The first run with 200 newtons load and the thicker component ran in 17 minutes, and the second one with 400 newton load also ran in 17 minutes. So we could post-process these results. Okay, so for this result with the thicker component, we can see that we do still have a stress concentration in this area, but the stress concentration is not as high. We've got a lower peak stress, and the deformation will also be reduced. So we could have a look at the overall displacement and see how that compares to the previous design. So we can see that we've now got a 0.2 millimeters displacement. So we've definitely reduced the displacement with this design, but maybe there would be further design iterations to go through. Okay, thanks for watching.